We're now going to graph the polar equation r equals 3 times the cosine of 2 theta. Once again, we go through our tests of symmetry. We'll start by checking for symmetry with respect to the polar axis. To do this, we replace theta with a negative theta, and we end up with r equals 3 times the cosine of 2 times negative theta, which is 3 times the cosine of 2 theta. The reason is because of the fact that the cosine function is an even function, so the cosine of any negative angle is equal to the cosine of the corresponding positive angle. So we have that the equation is going to be symmetric with respect to the polar axis. Now we can check for symmetry with respect to the line theta equals pi over 2. So what we do here is we replace the angle theta with pi minus theta. So now what I'm going to do is a little bit of simplifying first. We get r equals 3 times the cosine of 2 pi minus 2 theta. To evaluate the cosine of 2 pi minus 2 theta, we're again going to use our angle formulas for the cosine of the difference of two angles. What we're going to end up with here is 3 times the cosine of the first angle, so the cosine of 2 pi, times the cosine of the second angle, cosine of 2 theta, then plus the sine of the first angle, 2 pi, times the sine of the second angle, 2 theta. Close the bracket. Now we have 3. The cosine of 2 pi is 1. So I have 1 times the cosine of 2 theta. The sine of 2 pi is 0, so I have plus 0. So the result is 3 cosine of 2 theta. Because this is equivalent to what I originally had as my equation, I have symmetry with respect to the line theta equals pi over 2. If you recall from rectangular coordinates, if we had symmetry with respect to the x-axis and the y-axis, we necessarily had symmetry with respect to the origin. The same type of idea applies to polar equations. I have symmetry with respect to the polar axis. I have symmetry with respect to the line theta equals pi over 2. Therefore, I necessarily have symmetry with respect to the pole. For that reason, it's unnecessary for me to perform that check. Now, what I'm going to do, because I have 3 types of symmetry, I only need to pick angles between 0 and pi over 2, and then use the symmetry to find the additional points on the graph. So, I'm going to go ahead and set up a table here where I'm going to pick angles between 0 and pi over 2. So there's theta, and there's r. So we're going to pick our friendly angles again, 0, pi over 6, pi over 4, pi over 3, and pi over 2. Now we use the equation, which is, again, r equals 3 cosine of 2 theta, in order to find the values of r. So, for example, when theta is 0, we get r equals 3 times the cosine of 0, so that's 3 times 1, or 3. When theta is pi over 6, I get 3 times the cosine of 2 times pi over 6, which is the cosine of pi over 3. The cosine of pi over 3 is 1/2, so I have 3 times 1/2, or 3/2. I'll just fill in the remaining values of r for the corresponding angles and leave it to you to verify the results. What I'm going to do now is plot these points, r comma theta, in the polar graph, and then use the symmetry to find additional points. So this is the graph that we obtain. Now if you look at this graph, you'll notice that here is the point, there's the angle 0, and then I have 3 units out. Or I have the angle pi over 6, and then I'm going to go 3/2. I have the angle pi over 4, and I have a radius of 0. I have an angle of, well, I'll just go right to pi over 2, and then I'm at -3. Now, because I know I have all three types of symmetry, when I trace in the curve, I have to make sure that I incorporate all that symmetry, and we obtain the graph. This graph is called a rose. It's a rose with 4 petals.